Hello, in this video we are going to talk about the QuickSort algorithm. As you might know that for sorting, for comparison based sorting algorithms, the best time complexity that is possible is n log n. Some of the algorithms that can provide this complexity for sorting are merge sort and QuickSort. You might have studied about merge sort earlier, and if you have studied about it, you might be knowing that though merge sort provides a time complexity of n log n, merge sort also has an order of n space complexity. So today we will be going to discuss about QuickSort, which guarantees with a very high probability a time complexity of n log n in average case, though it has a worst case time complexity of n square still. But even with this time complexity in average case of n log n, it has an order of 1 space complexity. It is with a very high probability that the complexity of QuickSort will never be to order of n square. In fact, this algorithm is so much efficient in practical use cases that the sort function of most of the languages uses QuickSort. Let us see how QuickSort algorithm works in practice. Let us take we have been given an array A, which is 12, 18, 15, 21, 19, 30, 4 and 70. At each iteration of QuickSort, we choose a pivot element and try to bring it to its correct position. Let us say that in our implementation of QuickSort, we always choose the end element of the array as the pivot and try to bring it to the correct position. What that means is basically we will try to put all the elements that are smaller than the pivot element to the left side of it and all the elements that are greater than the pivot element to the right side of it. So suppose 17 is the pivot, then the elements 12, 15, 4 should come to the left. So let us say that 12, 15 and 4 are on the left and the elements 18, 21, 19 and 30 will be on the right. 18, 21, 19 and 30. Now we can see that the problem reduces to sorting the part of the array that is on the left side of the array and sorting the part of the array that is towards the right side of the pivot element, as the pivot element 17 is now at its correct position. Let us repeat the same procedure for the subarrays on the left side and the right side. So for the left subarray, we will be choosing 4 as the pivot, as that is the rightmost element of this subarray. So now we will try to bring 4 to the correct position and the array will change to 4 will come to the correct position and 15 and 12 will go to the right side of it. There is no element lesser than 4 in this current subarray, so there will be nothing to the left of 4. Now this problem further reduces to one subproblem of sorting the subarray of 2 elements, that is 15 and 12. Now we will choose 12 as the pivot because it is the rightmost element of this subarray and there is nothing lesser than 12, so there will be nothing that will come to the left side of 12 and 15 will come to the right side. Now we see that all these subarrays are of size 1. That can be considered as the base case as they seem to be sorted, as a subarray of size 1 is inherently sorted. Okay, this 17 is coming as it is to the correct position. We will be going into detail of how we won't need extra space to sort this, but we can see that we are doing the swapping within the original array. How this is implemented in the code will become clear by the end of this video. Let us repeat the same procedure for the right subarray. Now 30 is the pivot. There is no element greater than 30 in this current subarray, so nothing will go to right, and 18, 21 and 19 will go to the left. Now the problem reduces to this subarray of size 3. Now we make 19 as the pivot. There is one element 18 that is lesser than 19, and there is one element 21 that is greater than 19. So now the problem reduces to 3 problems of size 1. This 30 is carried as it is, and now if we see, we have the complete array as sorted. So let us repeat what exactly happened in QuickSort. In QuickSort, at each step, we chose a pivot element. Basically, the element that we try to bring to the correct position is known as the pivot element. So in this case, 17 is the pivot. Here 12 was the pivot. Here 30 was the pivot. Here 19 was the pivot, and so on. So at each step we choose a pivot element. How we choose the pivot element is dependent upon the implementation of QuickSort that we are doing. In this case, we are always choosing the rightmost element. There is also a version of QuickSort that is known as Randomized QuickSort, where we randomly choose any of the index of the current subarray as the pivot element. And how we implement this randomized quicksort is basically by choosing a random index as the pivot element. We swap that pivot element with the rightmost element so as to ensure that our code implementation remains the same. And also for the rightmost element, the code implementation is quite easier. Okay, so now at each step we have chosen a pivot element. The next step is we bring all elements smaller than pivot to the left side of pivot, and similarly all elements that are larger than pivot to the right side. Basically, this process can be called as partitioning of the array, such that pivot is at its correct position position. Now you might be wondering, is there any specific order in which we arrange the left and the right elements? Technically, no. So the only requirement is that 17 should eventually end up at its correct position. Whatever is the order of the elements on the left and the right doesn't really matter to us and is free for the implementation to do it as it likes. Okay. Now once we have partitioned the array, we can recurse for the left and the right sides. So basically, we can now recursively sort the left and the right side from the pivot index. So we can say that QuickSort is also a recursive sorting algorithm. Now, as is true with each of the recursive sorting algorithms, there should be a base case, right? What is the base case for QuickSort? It is clear to see that when the size of the array under consideration is 1, that is a base case. Great. Now let us try to run QuickSort and analyze it on an example and see how this will work. So let us say that our function will be called QuickSort. That will be given the array, and that will be given the start and the end index. Why the start and end index is important to us is so as to not create new copies of the array and to reduce the space complexity to order of 1, which is constant. Now let us say we have a partition function with us, which also needs to be passed the array, the start and the end index, and this returns us the index of the pivot element. So for example, suppose for the above input it was passed the array A and the start index 0 and the end index as n minus 1, which for this case will be 7. So this should return us the pivot index, which will be for this case 3, which is the new index of the element 17. Okay, so now as it has passed us the pivot index, it has brought the pivot element to its correct position, and now we need to recursively sort the left side and the right side of the array. So we can do quick sort the array, the start, and what will be the left side ending? It is pivot index minus 1. Similarly, the right side can be represented by array, the start will be pivot index plus 1 and the end will remain the same. Now what about the base case? The base case can be considered as if start is greater than or equal to end. In that case we can just return, basically we have nothing to do. Why greater than and equal to? If start is equal to end, that means the array is of size 1. Okay, now what if start is greater than end? If start is greater than end, that means it is an invalid array. Can that happen? Yes, that can actually happen. Why? Let us see in the above example when we pivoted at 30. We found that pivot index was actually the last index of our array. So now the pivot index will be 7 and we will be sorting from 4 to 6 and 8 to 7 because 7 is the end index and 4 is the start index of the previous recursion. This is an invalid pair and this case will be taken care of by the implementation that we just did. Now the problem reduces to how will we be implementing this partition function. Let us try to partition the above array only for the element 17 and see how this will work. Let me write the above array again. The array A was 12, 18, 15, 21, 19, 30, 4 and 17. Let me index this array as well. Now we know that the pivot index is the last index, so in our partitioning function we will be given this, we can find this n minus 1 or basically end as the pivot index. So our pivot element will be 70. Now we create a pivot index variable which will be initially to start. So initially it will be equal to 0. Now we run a loop. We run a loop from start to n minus 1, both inclusive. So basically in the above case the loop will run from 0 to 6. At each iteration of the loop we'll check if the element at index I is less than or equal to the pivot element. If that is less than or equal to the pivot element, we swap the element at AI with the element at pivot index, and we increment the pivot index by 1. Let us see how this will run. Now what we see is initially 12. Is 12 less than or equal to pivot which is 17? Yes, it is less than or equal to 17. So we swap 12 with the pivot index. Pivot index was also 0. So we swap 0 with 0. So 12 will remain here only. But now our pivot index will change to 1. Okay. Now our I is also 1. We see if AI, that is 18, is greater than, is less than or equal to 17. No, it is not. So we don't do anything. Now our pivot, so now our I will be 15. So basically I will be 2 and the array at 2 will be 15. Is 15 less than or equal to 17? Yes, it is. So we swap 15 with array at pivot index which is 1. So we swap 15 and 18 and the array changes to 12, 15, 18, and the pivot index is also incremented to 2. It is incremented by 1 and is now 2. Now our I is 3. Is array 3, that is 21, less than or equal to 17? No, it is not. So we move ahead. Is 19 less than or equal to 17? No, it is not. Is 30 less than or equal to 17? Again, no. Now when we are at index 6, when I is 6, we see that 4 is less than or equal to 17. Now as we have to swap array 6 with array at pivot index which is array 2, we do this swap. So now 4 will come here and 18 will go here. Also our pivot index is incremented by 1. So now the pivot index will become 3. Finally, we are at index 7. So our loop had to end at index 6. So we have ended the loop. Now finally, what we do is that we swap pivot with the element at pivot index. So what we basically do, we swap array end with array pivot index. So now array end is 17 and array pivot index is 21. So we swap 17 and 21. So our 17 will come here and 21 will go here. Here we are not incrementing the pivot index. So we can currently see that at the end of this iteration, pivot index will be pointing to the position of the pivot element which is 17, and the parts of the array to the left side. Each element to the left side here is greater than 17 and each element to the left side is lesser than or equal to 17. In this case there was no duplicates, so it is strictly lesser than that. And finally we can return the pivot index as that is the position where our pivot exists. That is it. So that is it for QuickSort. In this implementation of QuickSort, we are always choosing the end index, the element at end index as the pivot. let us just do a brief discussion about randomized quicksort as well. In randomized quicksort, we don't do any change other than in the partitioning function. So suppose in the partitioning function, we are given the array, we are given the start index and the end index. Now we choose a random element from between the start and the end position as a pivot element. So we can choose a random index from start to end, both inclusive, as our pivot index. Now we swap the element at end index with element that we want pivot to be, and then after this we run the exact same code as we had for the partitioning function of the normal quicksort. So suppose we had decided that instead of 17 we can randomly make any element the pivot element. In that case, suppose we had decided 19 we want to make a pivot, so we would put 19 to the last of the array, and then this case becomes same as when we chose the rightmost element of the array as the pivot. Hope you learned from the video, and make sure to subscribe to the channel to keep updated about more videos on various data structures and algorithms. Best of luck and see you the next time.